on Venus and you got really hot and you want to jump in a lake and have a nice cool swim, you'd be jumping in molten lead. And our planets are quite a bit hotter than that. There's molten lava, so the temperatures are above that, and so what you're seeing in all these planets, they glow. They are self-luminous planets. They're that hot. And many of the planets that you hear about, that have been discovered, particularly if they're ground-based, basically are extremely hot. So what we've got here are these two at a temperature well above the melting temperature of gold. We've got Kepler 4b quite hot, 5b and 8b above iron. So if you were to look at these planets, and the spaceship came to visit, you didn't want to land, but you wanted to look, it'd be like looking into a blast furnace. So next time you look into a blast furnace, you can simulate looking at these planets. This one is particularly interesting, however. It's very hot, it's very small. It's the size, in fact, of Neptune, and we'll talk about that. So let's talk about what we're finding from these giant planets and these smaller planets that tell us about our own planets. What we have here is the planet density, grams per cc, log scale, and we have the planet mass. And what we have is a yellow curve. The yellow curve is a theoretical curve. It says if you have a self-gravitating hydrogen-helium sphere, what is its density as you pour more and more mass in? And the answer is you pour more and more mass in, it comes along this curve, and finally it forms stars. That's how you form a star. But our planets, in red, are below that curve. So the density of these planets is less dense than hydrogen-helium, which is the least dense of all the elements in the universe. So that's a sort of a surprise, too. The other circles here are other ground-based measurements which we confirm that there are lots of planets that have densities lower than hydrogen and helium. So again, the theoreticians need to think about the equation of state for hydrogen and helium. And we need to think about our measurements and how good our measurements are, because you can be fooled. You can be fooled in the size of the stars. And I've mentioned that because we take that very seriously. When we talk about other planets like Jupiter and Saturn here, what we see they are quite a bit more dense. As you'd expect, they have metals. Metals for an astronomer is anything that's other than hydrogen and helium. So carbon, oxygen, and nitrogen are all metals. But what we see is 4b over there next to Neptune. And we see a couple of other discoveries. These are our planets that we think are different, fundamentally different than hydrogen-helium spheres. They have enough metals in them, so you might have a core. Now the core, because you've got hydrogen-helium as well, might have dissolved. So you've got sort of a coffee cup where the sugar, in this case, is the core. The core is dissolved. We don't know. But one of the interesting things is our 4b discovery, which has the same density and same mass as Neptune, is so close that it's molten. It's hot. The irradiation from the star is 400,000 times as much as Neptune gets. And so you would expect that planet would have inflated and expanded like one of our Jupiter-like things. But it didn't. Something is different here. We don't know what it is. But again, another mystery that helps us understand our own planetary systems. Why are some like Jupiter? Why are some like Neptune and Uranus? And of course, we're all interested in the ones here at Earth. There's one object there, about 7 times the mass of the Earth, very, very hot. Again, it's molten, that the Corot mission was able to pick up, 7b. It's a French mission that launched before us and has found what we believe is a rocky planet. Certainly nowhere near the habitable zone, however. So in this year, we are observing our field of view is up. We are looking at several hundred of these candidates to see which ones we can recognize as prove our planets. And when we finish the spectra, we do the modeling. We will then announce discoveries, probably either December in January is when we get all the data put together and understood. One of the things I'm showing here is that when you look at a star, you can actually see the oscillations. Every star, including the sun, pulsates. By looking at the pulsations for a star like the sun are acoustic modes. So if somebody asks you, what's the structure of the inside of Earth, How do you know? Nobody's drilled down that far. Acoustic modes, we call them seismic waves. Stars have similar things generated by their spots and the storms that are associated with the spots. And we can look at those acoustic waves, and you can actually see here, these are the frequencies of the acoustic waves, and you can see the spectra here blown up for us for 3 different stars. And the acoustic waves are very, very clear. Our astroseismologic colleagues say we will be able to do very, very well in terms of getting sizes of planets to a couple of % quite often for the brighter ones. Not for the dimmer ones. For the dimmer ones, we have to do astroseismology. I'm sorry, we have to do astrometry. The other thing is, of course, we'd like to understand our planetary systems. How old are they? Planets form with their stars, so you need to know the age of the stars. One of the ways of doing that is to say, when you form a star, all that angular momentum from the contracting gas spun up that star, so it's rotating at a very high rate. Over a period of time, it dumps that angular momentum in a wind and slows down. So if you can calibrate its rotation rate and you can measure its rotation rate, you may be able to get at the age. Now, people have done that for a long time. They look at a couple of clusters of stars and they say, well, we'll generalize from that to all the stars and make up and come up with a relationship. That's shown here. That there's only 2 clusters that you can do from the ground. So you've got data along this. This is the temperature, B minus V. But basically, that's hot, that's cold, and this is age along this axis. That's old, this is young. And we've got 2 clusters to calibrate the entire surface with, plus 1 spot. The spot is the sun. And we've got to calibrate this entire surface. Kepler looks at a cluster, these 4 blue clusters, and will give us a much better interpolation routine, so we'll be able to tell how old these planetary systems are. And over a period of time, planetary systems change. They tend to throw their planets either into the star or out entirely. So again, something we'd like to know about. One of the things that you find when we can measure things 100 times better than anybody else has ever been able to measure are strange things. Here is some data, and this is a light curve from some 30 days. That's heliocentric Julian day, so that's it's an heliocentric Julian day. But you can see the data. You can see the nice, what look like transits at first. You fold the data. It's beautiful, nice and flat here. Nice curve here. The shape is just right. But that is that's the occultation. The planet goes behind the star, or the object goes behind the star. It's perfectly flat. The depth is greater than the amount of light blocked when the planet or the object moves in front of the star. Now, how can that be? This companion, we know the size from the dip, and that's the amount of change in radiation, sigma t to the 4th. I mean, we all learned that in sophomore physics. That's the flux from it. We've measured the flux, so now we can measure the temperature. The temperature of this object orbiting the star is 12,000 Kelvin. The star is at 9,000 Kelvin. The companion here is hotter than the star. Now, clearly, you'd get a great paper if you were able to prove that the cool star was heating the hot planet. That would have reversed thermodynamics, and you'd have a great paper. We haven't tried that. We've tried other explanations, and we're not sure what this is, and we find more than one of these, and we find a lot of other strange things. Our concept right now is that since most many stars start out as 2 stars orbiting each other, and they don't have exactly the same mass. You can imagine a star like an M dwarf or K dwarf, stars that essentially live forever, orbiting a star that's hotter than the sun, that doesn't live forever, that lives for 500 million years, an A dwarf. And so the A dwarf lives out its life, burns through all of its hydrogen very quickly, and its atmosphere starts to expand. It becomes a giant, like the sun will someday become a giant. That hydrogen then is dumped on the small star. The small star grows and picks up all this hydrogen, and it becomes a hot star. It becomes a star that's almost as big as the A star. And all you're looking at then is the cooling core of this dead star. Possible explanation. People don't know what the answer is yet, but that's one of the explanations I've heard, and certainly it's one I think I like the best. I'm going to show you something that's on Astro PH. It's caused a lot of controversy, and you need to keep this in mind. It's extremely important. We've only found 5 exoplanets. No matter what anybody says, that is the truth. We found hundreds of candidates, and we can start looking at these candidates and ask, well, if half of those are false positives, which is our usual false positive rate, the rest of them are probably could be planets, and we can begin to look at their distributions and say, what can we learn from the distributions? What I'm going to show you then are some of the results from Planetary Candidates based on 33 days of data. They're going to be based on the 312 candidates that were released to the public in June. We released that data. We released the data that these are candidates. Any of you, starting in June, can look at these candidates. We've told you the RA and the DEC. We've told you the magnitude of the star. We've told you the epoch of the transit. We have told you everything we know about these planetary candidates. It's out there for people to go and discover. We are not, that is, the mission is not spending any significant amount of time on them simply because we've kept back 400 bright ones because we've got time on the Keck telescope and the HET and the telescopes and the Canary Islands and Texas and Arizona, and we're trying to get as many of these done as possible so we can announce planets this winter. But they're out there, and this is what we'll be talking about. All the candidates get released in February. There will be none that are held back. So we've picked off the smallest candidates so we can try to do them ourselves this summer, get them done. And the stars are all dimmer than 14th magnitude because it's easier to do the bright ones than the dim ones. People have, however, done stars about 15 times dimmer than this. So it's quite possible for you to go out and do that. I'm going to tell you up front, we do not have any Earth-sized planets in the habitable zone. We get that question all the time. You need 3 transits. A transit orbital period is a year. We've been up there a year. We can't possibly have 3 transits for planets in the habitable zone that are Earth-like. So, if the press asks you, do we have such things? The answer is it's impossible. Could we have planets as small as the Earth? Sure, but they'll be very, very hot. The orbital periods are short. And so we'll talk a little bit about that. Here is a distribution that has been shown on Astro PH. What we have got on the scale to the left on the upper panel is a number of candidates. It is not the number of planets. It's the candidates. The planets, there are only 5. We showed you them. But what you see is the planet radius to the right, or in this case, the candidate radius to the right. And what you see there is we don't have a lot of candidates that are big. We have a lot of candidates that are small. We have a lot of candidates that are smaller than Neptune. Well, what's smaller than Neptune? I think you can figure that out. Below what we have are the distributions that are published for all these planets people have found that are ground-based. And this has a very large peak, around 12 or 13 times the size of Earth. And those Jupiter, by the way, is about 11.2 times the size of the Earth. So these planets that people find on the ground, and they find over 400 of these, are generally Jovian-sized planets. And they find them because that's the easiest thing for them to find. For us, they're still the easiest thing, but we just don't find very many of them. Our curve is very low at the large sizes. So the implication of this curve is that there's very likely to be an awful lot of small-sized planets, which is, of course, what we're all hoping for, that there will be a lot of small planets. And so this, to me, is a very positive thing. It doesn't prove anything yet, because these are candidates. But by the end of the year, we ought to know which are candidates and which are planets. So something I think is very